Our next video is going to focus on the Clausius Clapeyron equation. And we've discussed vapor pressure and delta H of vaporization, and we know that these depend on temperature. So how can we put these in a nice, convenient way to analyze? So if we would plot vapor pressure versus temperature, we kind of get these exponential curves. And we've talked about this before, and exponential relationships are not very good. They're hard to be able to predict, and as chemists, we like to see things linear. Okay, so what Clausius and Clapeyron did was they tried to come up with a linear relationship involving the vapor pressure and the temperature. So instead of plotting the vapor pressure versus the temperature, they went on the y-axis and plotted the natural log of the pressure versus 1 over the temperature. Okay, and typically the relationship we're going to see looks something a little bit that looks like this. And the slope of this line is going to equal the negative delta H of vaporization divided by some type of constant, which happens to turn out to be R. So the Clausius-Clapeyron equation shows the relationship between the vapor pressure, the temperature, and the delta H of vaporization. So this is a very, very powerful relationship. And they found that by plotting the natural log of pressure versus 1 over the temperature, we see a linear relationship. Okay? Linear relationship, y equals mx plus b. Basically, they showed that the natural log of the pressure is going to equal negative delta H of vaporization divided by R times 1 over T plus some constant C. And here R is going to equal 8.314 joules per mole Kelvin. And this is a different value of R that we've been using before, but we can convert the units and we find that they're the same number. Typically delta H of vaporization are represented in kilojoules per mole, so this is a more convenient way to represent R. Okay? If we would make this in y equals mx plus b form, we find that our y variable is the natural log of pressure, m, which is the slope, is the negative delta H of vaporization divided by R. The x variable is 1 over the temperature, and the intercept is this constant C. Okay? This equation is more useful in something called a two-point form, where if we rearrange this and looked at 2 points on this particular graph, we can rearrange this to say that the natural log of P2 divided by P1 is going to equal the delta H of vaporization divided by R times 1 over T1 minus 1 over T2. And this relationship right here is going to be very, very powerful to compare various values and look at experimental data and determine what our delta H of vaporization might be. And make sure you're able, I know it may have been a while for some of you when you're looking at natural logs and trying to solve an expression with 1 over T1 and 1 over T2 in parentheses where we're subtracting each other, but make sure you're able to manipulate this particular expression right here and be able to solve problems using this two-point form of the Clausius-Clapeyron equation. Because like I said, this is going to help us relate the vapor pressure, the temperature, and the delta H of vaporization, which are three very, very important aspects of looking at this. So you'll use this most especially when it comes to the labs that you're going to be performing this semester. And make sure you know this expression right here, because it can become very, very useful in solving problems.